Okay. If we take a look at this table here, of all these KSPs, and we pick on Sabina, which compound would you say in that KSP table, Sabina, is the most soluble? It'll dissolve the best in water. What would you say? Yeah, go by the exponent. So are we looking for the biggest or the smallest? Right? Because what is KSP? These are KSPs. KSPs are always what over what? Well, any K is products over reactants, right? So are my ions on top or on bottom for a KSP reaction? The ions are on the top, right? Because they're the product. So you would want a really big KSP if you want a lot to dissolve. Now, none of these are very big, but one of them is bigger than the rest. There's a number bigger than -5. -3 for what compound? Silver acetate. I'd say this is the most soluble compound in that table. Okay, so that's kind of how you read this stuff. But even it's not very soluble, right? 10 to the -3 is a equilibrium constant. Okay, I added this table. You don't have it.
Wait, silver acetate is what again?
This is the most soluble. Just looking for the biggest KSP is all. Just playing around with that. So we are going to try to predict whether a precipitate's going to happen or not. And they're going to give us 2 beakers, and we literally just dump them together and predict. Well, it'll be a lot easier to make these predictions, I think. I mean, if you have a photographic memory, you're set. You know all the solids, right? But I'm not a member of that lucky group. So I just know 2 general rules, and then everything else falls into place. Let's see if we can figure out one of those rules are. Gabby, there's some cations, and you never, ever form a precipitate with these cations. What were they? What cations were they? Remember, cations are positive or negative? Positives. Which cations were they? And remember, me harping on this? The alkaline metals, right? So that's group what? Group 1. So whenever you see lithium, sodium, potassium, those are the big 3. Stop there. Okay. Now there's one more though. And if you're really good with your solubility rules, you'll know this. Otherwise, it's a tough question. It's a polyatomic cation. I think it's the only polyatomic cation that we know of, that we named. Calcium is a calcium plus 2. That's only one atom. Carbonate's an anion. I'll give you the first letter. Ooh, NH4 with a ammonium. Never formed precipitates with any of this stuff. That's just burned into my memory because I've done this so often, and it's just, life is so much easier if you remember this. Okay, anions. I can only really think of one right now. One biggie, and it's polyatomic. And this is a really hard question for you to recognize. Nitrates. You'll never form a precipitate with those nitrates. All I'm saying is iron 3 nitrate. Doesn't matter. If you see nitrate, can't form a precipitate.
But I mean, like, because for the cations, it's for like most of the anions are not.
Nope, they'll all form precipitates at some point or another. But nitrate won't. I'm going to skip the animation because it locked up my computer last time. So we're just going to jump to the homework. This is the homework. They're going to say 2 solutions. We have 25 mils of potassium phosphate, and we have 55 mils of 0.2 molar magnesium carbonate, just making stuff up. Will it precipitate form? That's the question we have to answer. So you mix these two solutions, and they give their concentrations and volumes. Will a precipitate occur? The answer is always yes or no, but you know you got to show your work, so it's a lot more than that. Here's the game plan. First, figure out what the heck the solid is going to be, right? And pretty much just using these game plans or searching out every possibility on here. It's a lot faster just to know these two rules, I think. But so figure out what the solid is going to be. Make your best guess for the solid, and then write its what reaction? We call this the KSP reaction. We call it the KSP reaction. And then we're going to calculate, well, we're calling it a QC expression instead of a KSP expression, because we don't know if a solid is going to occur or not. And if there's no precipitate, you don't have any equilibrium going on. This stuff just dissolved and is just sitting there. You're not forming a solid. So what we're going to do is calculate the concentration of our cation and our anion there, our B and our C, raised to its stoichiometric coefficients, right? Calculate it. And then we have three possibilities. Now, first, we're going to have to find the KSP for this solid we guessed. And where do you get that stuff? The table. Yeah, you don't have to memorize that stuff. So get in the table for it. And then there's three possibilities. Either the QC we calculate, they call it the reaction quotient. You're going to nail KSP. It'll be too small or too big. So which possibilities would you say, Diana, you're going to get a precipitate? Which ones? I don't know. It could be more than one. Good. When it's greater. Perfect. Because then you have too much product. And remember, the ions are the product. You have too much ion. It has to go the other way, Le Chatelier's principle, and form the solid. Definitely. QC is too big. Everybody agree everything else is no? If QC is less than KSP, definitely no. This one, you could argue with me, and I guess I could go either way. But technically, if you nailed KSP, you probably can't see it. But there is a microscopic hunk of solid in there somewhere. And it's not going to look like a precipitate at all. It looks just like it did before. But microscopically, there has to be a little tiny hunk of solid. So really, the technical answer here is this is yes, too. So there's really are two yeses. Okay, so that's the game plan. Guess what the solid's going to be, and then calculate a reaction quotient for the KSP reaction. We'll do a couple of these together, and then we'll go to the boards, and this hour's going to go so fast and so much fun. From each of the following ion concentrations in a solution, predict whether precipitate will form in solution. Okay, so here they're starting us out easy, because notice, look what's coming up. They're giving us volumes and concentrations. So we're starting out with just one baby steps here. What would be the solid? Because Monica, remember, we're supposed to guess what a solid is going to be, its chemical formula. PB. All right. What would be the formula? PB with a what charge? All right. It has a positive 2. And what anion do you put it with? Cl. And that has a what charge? Negative. So what would be the formula for my solid that I'm guessing here? PbCl2. Right? So, Monica Soto Ruiz, how do I finish this KSP reaction? Monica Soto Ruiz, there's, oh yeah. I was picking on Monica, yeah. PB plus 2? Picked on you twice, I'm confused. PB plus 2 and but how many of them? 2 of them. Okay? So we write our not KSP expression, our QC expression. Tegan, what would it be?
It would be 0.35
0.035.
times 0.15.
Perfect. All over 1. What do we get here? 0.035 times 0.15 squared. I got about 7.9 times 10 to the negative 4. But we have to look up a KSP for this. If we go back to this table that you don't have, where is it? Here's lead chloride. 1.6 times 10 to the negative 5. Where'd it go? My KSP is 1.6 times 10 to the negative 5. So, Jarixa, will there be a precipitate? Yes, because QC is greater than KSP. Exactly. QC is too big. So definitely yes. Okay. I don't think there's going to be very many homework questions like that. They're going to almost all look like this one. Okay? So this one let's do together, then we'll get you moving. Okay. Jasmine, we're dumping in 45 mils of 0.0015 molar barium chloride into another beaker that has 75 mils of 0.0025 molar potassium fluoride. Okay. So remember the game plan. You got to figure out what a solid is. What solid would you guess it's going to form? She says BaCl2, right? It fits the 2 rules. It fits the 2 rules, right? There's no potassium, there's no group 1, and there's no nitrate, so it fits those 2 rules. And you can go look at the table, and you're going to see that it's not there. All right, it's not there. There's no barium chloride. But you really didn't have to go look at the table because barium chloride is a solution. So just by it having a molarity, they're saying, no. He can't form, he's not forming precipitate. So just by him being in this, all right, so don't pick him. So don't pick your solutions. So Alyssa, don't pick KF. Yeah, because it's a solution, right? So which one, what possibility could you pick here?
You said don't pick KF?
Yeah, because, right?
You just said BaCl2 is not on the
Yeah, so, and BaCl2 is a solution. KF is a solution. So you don't pick the solutions, because they're never the, otherwise it can't be a solution. Does that make sense? Don't pick a solution. If I tell you 0.82 molar blah,
so just
this can never ever be your precipitate because it's a solution. That's 0.82 molar. It dissolved. Otherwise you can't make 0.82 molar. Does that make sense? So don't pick BaCl2, don't pick KF. So what's left to pick?
the 45.09.
Ah, what ions do you have available to mess with here? You have,
Okay, the Cl2?
when you see this, whoa, you guys don't see it. When you see this, what ions are you supposed to be seeing? You're supposed to be seeing Cl minus ions, and what else? Ba plus 2 ions. Okay. When you see this, what ions are you supposed to see? K plus and F minus. Okay. So these are your choices. You can combine, but it has to be a cation with an anion. And remember the general rules. Don't pick alkali metals. So let's not let Alyssa off the hook here. No, what's the solid? What? Combine a cation and an anion and make it a solid, and just guess. Ba barium and the F minus. That's your only choice in this, is the Ba plus 2 and the F minus. Does everybody agree? That's your only choice, is the Ba plus 2 and the F minus. Now, I like writing those charges in there because if you don't, you're going to write the wrong chemical formula. Those stoichiometric coefficients are so important for KSP reactions. So what's the chemical formula for my solid? BAF2 with a little s. Okay? So when you're trying to pick out these precipitates, right, what solid am I going to write a KSP reaction for? Don't pick the guy behind the big M, right? Because he had to make a solution. That can't be one of your answers, right? So you either got to combine this cation with that anion, or that anion with this cation. Okay, exactly. Okay? So how do I finish this KSP reaction? Ba plus 2 plus 2F minus. Okay, now I need a QC expression. What would I write for my QC expression, Crystal Zamora? Oh, Crystal, hang on. Before we go do this, you know what I think would be a good idea? Because you're going to have to look up a KSP sooner or later anyway. Let's do it now, because then it's insurance to make sure we wrote this thing right. Right? So is there barium fluoride in there? And if there is, what is the KSP? Do you see it? What's the number? Okay. 1 times 10 to the negative 6. We needed it anyway. So I think it's a safe time to look it up. After you make your guess, 1 times 10 to the negative 6 for barium fluoride. And notice how we even wrote the formula right? Right? BAF2. So that's a good check. You have to look it up anyway. Okay, I kind of cut her off there. Allison, how would you write your QC expression? It's products over reactants. We can't put in numbers. We're just going to put in brackets, because that means what units? Molarity. Okay, keep going. Squared all over 1. Okay, let's see if we can get one of these. So Danny, the concentration of anything is what over what? Moles over liters. Sometimes I think this is really hard to recognize, that units are really an equation. Divide the number of moles by the number of liters, and you'll have molarity. Like density. Divide the number of grams by the number of milliliters, and you'll have density. Molecular weight. Divide the number of grams by the number of moles, you'll have molar mass. Okay, so we need the moles of barium and the liters of solution. Diana, do you see how to get one of those? Which one? The moles? The moles? Okay, how would you get it? Good. Turn that into liters. That'd be 0.045 liters. And then do what with it? Excellent. Multiply by the 0.00, multiply the concentration. Notice that whenever they give you a volume and a concentration, you know moles, just multiply the two. So we'll have 0.045 liters, 0.0015 moles per liter. Liters will cancel. We'll end up in moles. How about the number of liters part? Crystal Munoz. How do we get the denominator? The liters of solution. Good. Yeah. Well, not 35, 75, right? We'll add, she said, turn these into liters and add them up. Exactly. So I'll have 0.045, whoop, 0.045 plus 0.075.
Why is it 0%? Oh, no.
I got 5.6 and 10 negative 4. So you're just dumping one beaker of solution into another beaker of solution. So your total volume, just add up the volumes. Okay, we got to do the same thing now for the fluoride. All right, it will be the number of moles of fluoride all over the number of liters. So do the same thing, calculate fluoride's concentration, put your results into the QC expression, compare it to KSP. Don't forget that darn fluoride is squared when you put it in your QC expression.
Other one squared.
Hopefully someone got, hopefully you got, did you get 10 to the negative 9? Oh, good. All right. Okay. So hopefully you got 1.36 and 10 to the negative 9. Now, if you got that, what's the answer to the question? Will you get a precipitate? No, right? Because QC is too small. No precipitate. Okay. So you try it now. Want to go to the boards, Sabina? Let's go to the boards. Get up and move. Get your blood flowing, right, Vivian? Yeah. Well, too bad. Just go. It's good for you. Right. Come on. Up, up, up. Right, Crystal, it's good for you. Then you guys can show each other how you're doing the problems, and it's so much more efficient.
Because the QC is smaller.
I'm not going to do this.
The answer is no.
Oh, I gotta move that. Let's do number 2, though.
Already started on.
All right, okay, that's okay. Let's just say what we were gonna do. Let's do this first one. Oh, you need the chart. Here's your chart. Do you want to go to the boards? Boards, Danny, it's good for you. You can show everyone how you're working problems. Tiffany, you don't want to go to the boards.
I don't have my book.
Oh, but I don't have it here either.
No,
Because people need the table. No way, you can't remember that question. Right there.
Do you add soda or times up?
If you're going to put in one beaker into another beaker.
So you plus.
Yep. Now for, which one are you doing? Okay. But for this one, you're trying to, which solid could you possibly be forming?
That's what I'm trying to figure out.
Yeah, you can't be sodium with anything.
It will be.
Remember? And it can't be nitrate with anything.
Fe and
It has to be Fe and the S.
let's
And then look at the formulas to see what their charges are.
Have your calculator out?
You see how to do these? So there's your moles, that molarity times. Yeah, yeah. And then now you get the liters, you have to add up the volumes. You have 65 mils and 40 mils. Yeah, because when you calculate the concentration of the other one, it'll be the same denominator, but different moles. Anybody got an answer yet for this first one? So 1 times 10 to the negative 6. So Ellison got about 1 times 10 to the negative 6 for QC. So did Tegan. So I think you get somewhere around 10 to the negative 6. Depends on your rounding. So everyone's not going to get the same answer, but around 10 to the negative 6 for your QC. Compare that to KSP, see if you get a precipitate or not. So you know how to do all this in one step on the calculator? So take this one times that times 0.035, hit equals, and then divide by, and do parentheses, 0.065 plus 0.04, close parenthesis, equals. And you got it.
I was scared to use those parentheses because they look.
It saves so much time.
Yeah, they just look scary.
No, it's. I think it's 1.6 times 10 negative. Looking at for lead chloride, right? Oh, it's 10 to the negative 5. So did you get a precipitate for number 17.52? I see a lot of no's, right? Good. Yeah, you should get around 10 to the negative 6 for your QC. If you didn't get it, just ask and I can help you out. If you did, try the next one.
What was the first one?
Around. So now you have to take this times this squared.
Squared.
Yeah. Yep.
Yeah, I should have put that. Okay, that's fine.
I think the hardest part is starting out on these guys. See if you can figure out what the solid's going to be. And you can always check the KSP table to see if you picked the right solid. So what solid's going to form for this one? Yeah, how would you write the formula? Mm-hmm. Fe has to be a plus 2. Mm-hmm. It's be FES. Good. I think most everyone's got number 2 going. It'll be just iron sulfide, iron 2 sulfide.
So what's the KSP for iron sulfide?
Oh, you need the KSP?
Yeah.
All right. Where is it? Here it is. 6 times 10 to negative 18 for iron sulfide. So will there be a precipitate? Mm-hmm.
QC is larger than KSP.
So that means there's too much product, too many ions. So it's going to have to form a precipitate.
Yes, precipitates.
Yeah. There's only about a minute left. You should get an answer of yes. Precipitate forms.